So today we are going to try out the Electude simulator. This is a trial version. You could call it the demo. I'm going to show you a few things that it can do, but these are just indicators of how powerful this learning platform is when it comes to bringing you near to real life scenarios. I've used this simulator for years, so I'll swear by it. It's quite very accurate. I actually tried this simulator before covering Electude classroom content, and everything that I had done in the field before I started using Electude, I found out that the simulator worked very much like real world scenarios, like what I saw in the real world scenario. So I trust it. In this case, because we are using the trial version, we are going to practice and experiment with a few things. We shall be using tools that are available in the demo, as you will see. There are two versions of this simulator outside the school. There is this demo version, which we are going to try. There is also the competitive version, which if you wish, you can go to the Electude website and log in. You need to get credentials, log in, and you can competitively use the simulator to troubleshoot vehicles. There is a competition going on over there. So we are going to do the trial version for now. This vehicle does not have a problem. On the competitive side, they always give you cars with unknown problems, which you have to solve in a very short time and accurately without changing parts needlessly. But with this version here, what we are going to do is I'm going to show you a few examples of how the simulator works. So we have a car in front of us with the front open, the hood is off, so that we can see all the components we need. The car doesn't have a problem, but while playing with it, I'll cause problems. I'll make problems, and then we shall see how the simulator reacts. We shall start with the dashboard. You need the dashboard to control the engine. Right now, the engine is switched off. So to start the engine, you turn the key like you would in a normal car to the crank position. I'm sure you can hear that. You can even rev it up. You can even rev up the engine a little bit. Yeah, if you get closer, if you zoom in and get closer to the engine, you can hear the sound. The engine sound is louder. Yeah, over here we have the engine computer. Up on top of the engine, you have the ignition coils. Lower here, you have the injectors. You have the engine wiring harness down here below. You have the alternator over here up top. What else can I show you? Have the coolant reservoir down here at the bottom, the battery, the airbox, various connectors. I believe this is for the intake air temperature. This is for the mass airflow. What else can I show you? This is a throttle valve. It's a module actually. Throttle motor control valve. It's a throttle control valve with a built-in module. We shall explore that later. Down here you have the cooling fan, air intake over here. Here you have the fuse box and some relays. We shall play with those later. And then we have the oxygen sensor here. I believe this is this connector. This is I'll find out later what this is for. You can unplug it and find out, but we shall see that later. I'm just saying these things out from memory. I think this is the EGR valve over here. This is the purge canister. Oh, I've disconnected it. I clicked. This is for the evap system, the evap canister purge valve. I've disconnected it. That won't stop the engine running, but if, for example, we pull out the diagnostic system, to do that we have to identify the vehicle first. This is the OBD2 diagnostic device. If we read codes now, I don't see any codes. I would expect codes, being that I unplugged this, but maybe the engine temperature hasn't reached a value. The engine temperature is shown up top here. Maybe it is waiting for the temperature to reach a certain value before it tests this evap valve. So that's why it hasn't brought that code yet, but we shall explore that valve, how it works later, at least electrically. Yeah, now if I switched off the engine and I went back and tried to identify this vehicle, this is the VIN. It gave it to us the last time we tried to log into the vehicle. But now if I try to log in, I'm going to, it's still giving us the VIN. Let me try to read codes. Yeah, it's saying communication not possible, communication not possible. Yeah, so, but at least it is talking to the gateway. I believe the gateway takes a while to go to sleep and stop communicating, while the other modules go to sleep almost as soon as the ignition switch is off. Try to identify the vehicle again. Yeah, it still gives us the VIN, which means the gateway is still awake. Let me try fault codes. It has no fault codes, which means it is alive. If we tried any other control module like the ECM, it won't communicate. Communication is not possible even with the throttle valve control module. Yeah, so let me switch the key back on, and you now see that if we go to all the control modules, if we try the engine one, for example, right now you can see it is communicating and it says there are no fault codes. We can check on live data. We can share coolant temperature. We can ask for that. Short-term fuel trim, long-term fuel trim, engine speed. Yeah, for learners, fuel trims may not be so important, so I'll uncheck those. Ignition timing advance, intake air temperature, airflow. I'll also put that on the list. The oxygen sensor, EGR control, no. Accelerator pedal position, maybe. Injector pulse width, yeah. Okay, let's play with those. Display the selection. Right now, because the engine is not running, if I played with the accelerator pedal position, you can see the values are changing. Look down here, accelerator pedal position. When I press the pedal, you can see the values are changing. However, nothing else is changing because the engine is not running. So let's get the engine running. Now, you notice that the coolant temperature is creeping up. Engine speed is still high because the engine is relatively, it's not cold, but it's not hot either. It's just warming up. But ideally, this should drop down, and you can see it is dropping down with every increment in temperature, engine temperature. The RPM, the engine speed goes down, drops down at idle, and then we have the airflow rate reading from the mass airflow meter. If we press the pedal again, you can see that goes up as well. Right. Oh, I was looking for the graph. The graphs are right here. You can see the colors. The engine speed is in green and the mass airflow is in blue. So let me go on the engine again. You can see the two are together. Yeah, so katika tutandika okuonoona. Let's try playing around with things. Let me disconnect this. Yeah, the RPM has shot up. I can see this, what is it? The accelerator pedal position sensor reading went up. So now, even when I depress the accelerator pedal, it's not responding. So this connection is for the accelerator pedal position sensor. I'm sure if I go back, in fact, even the injector pulse width is not changing because the computer now doesn't know what I'm doing with the accelerator pedal. So if I'm going to connect it again, but it's not working yet. Why? Because the car went into fail-safe mode. The computer went into fail-safe mode. If I were to switch off the engine and then let it run again, you can see it is now responsive. It has now got out of fail-safe mode, but you can see the data. Yeah, but if I went back to fault codes, I will certainly find a fault code for the accelerator pedal position. I'll need to take a phone call. Yeah, so let's continue. You can see we now have fault codes for the accelerator pedal position. Even the idle went haywire. Yeah, so yeah, all that is coming from me playing with this not playing, disconnecting the accelerator pedal position sensor. So I think you've seen enough of that. Accelerator pedal position. What else can we play with? I'm going to leave the fault code in the diagnostic machine in that position so that let's actually clear these fault codes because we've plugged the APP back in. So now there are no fault codes. Now let's unplug something else. Let me play with the oxygen sensor, for example. That. Yeah, you can see the codes are there now. O2 sensor circuit. In fact, the check engine light has come on, if you notice. So there are codes to do with the oxygen sensor. System tooling, no activity detected from the O2 sensor circuit. and so on. But you can see these codes are now listed as active. If I plug the sensor back in, I've now plugged it back in. We'll go back, read the fault codes again. You see they are no longer active. They are in the history. They are in the history of the engine computer. So engine is still running, but see the check engine light has already gone off. If I unplug this again, do you see this? The check engine light is off. If I unplug the sensor, the check engine light goes on immediately. The codes, the diagnostic machine does not display they are active. I know they are active in the engine computer, but we have not asked the engine computer. We have not told the diagnostic machine to ask the engine computer for an update. So how do we do that? Go back one step and then ask for the codes again, and you see now they are on the active, that these codes are now active. Yeah, so let's reconnect that oxygen sensor. Check the fault codes again. They are still there, but they're in the history. Clear them, and you don't have anything now until, of course, you get a problem with that circuit again. This, I believe, is, let me check, I think this is a crank position sensor. If we unplug this, I believe the engine will stop running because the engine computer will not know what position the engine is in. So let's do that. Yeah, the engine has shut down. Yeah, so if we went back and updated the fault codes, you are going to see, oh, engine coolant. It's saying engine coolant temperature circuit high input. Let me try to crank the engine again. Yeah, it has gone into safe mode, but you can hear the fan is now running, the check engine light is on, the coolant temperature gauge is not reading, and you can hear the fans have gone on. This is now in fail-safe mode. The fan is over here. If you put closer, you can hear it. Yeah, so let's reconnect that engine coolant. Yeah, you can see the gauge is now reading correctly. The check engine light is still on. Oh, it has just gone out. And it says here the code is still active, but we know it isn't. If we go back and read the fault codes, it's now in the history. Those codes are now in the history, at least the one for engine coolant temperature and the one for idle. Remember when we reconnected the coolant temperature sensor, the idle kind of got out of control, and then the computer regained that control. That's when it set this code. So let's clear the fault codes. There are no fault codes right now, and everything is good, and you can hear the engine coolant. No. The cooling fan is off now. It's just the engine running. Yeah, this is the cam sensor. Let's unplug that. Check engine light has come on, but the engine continues to run. Yeah, this engine can continue to run without the cam sensor, but not without the crank sensor. So if we went back and checked codes, you can now see one for the P0342 camshaft position sensor circuit low input. So if I put it back, in fact, before I put it back, let's see if the engine will run, will crank and run without that sensor. Yeah, it will. It will somehow run, and so let's connect the sensor back again. Yeah, the coolant temperature has reached. Yeah, I hope you had the fan come on and then off again a moment ago, because the engine warmed up to the limit and then the fan kicked in and then the engine cooled again and then the fan went off. That's normal operation. It would happen especially if you are in slow moving traffic. Let's go back to clearing fault codes. We read them. They are now the one for the cam sensor is in the history. Clear it. We don't have any faults right now. I'm looking for the crank sensor. Where is it? This is the crank. These are injectors. This is the coolant temperature. Crank sensor, where are you? Is this the crank sensor? If it is, when I unplug it, the engine will stop running. Yeah, and it has. Let's go back and read fault codes. Yes, so P0337 is now there. It's active. Crankshaft position sensor circuit low. If I try to run, well, it will not start. It will not start without that sensor. Yeah, so let me put the sensor back. Try to run the engine. It should run now. It ran, and you saw a moment ago the check engine light went out. So if we go to fault code, we are now in history, and I'm going to clear the code. Let's play with one injector, maybe injector 3. We are now closer to the engine, so you can hear the engine is louder. Unplug injector 3. Engine is still running, but you can hear how it is struggling. That's called a misfire. So if we look at the codes now, we are going to see, did I leave the oxygen sensor disconnected? It's still connected. Yeah, so we see code for signal number 3, and also the code for injector circuit open. So let's put the injector back. You see it normalizes. It's the same thing if you disconnected the injector number 2, you get the same effect. If you disconnected 2 injectors, the misfire is worse. The engine is barely able to continue running. If I disconnect the third one, the engine will definitely die like it has now. And you are now going to have fault codes for misfire on cylinders 2, 3, and 4, and also injector codes for those cylinders. You can see the list of codes over there. Also, you have a code to do with the idle engine speed, because the computer was struggling to maintain ideal RPM. So the engine will struggle. In fact, it won't start with just one cylinder, because only one cylinder is now functional, cylinder 1, because the other 3 are not getting fuel. So if we connect one, it may start, but you can hear it is running very poorly. Let's connect injector number 3, better, but still with the misfire. Injector number 4 restored. Now we have a good engine. So now let's clear those faults. You have no faults now. We can also play with the ignition coils. Let's play with ignition coil number 4. Same effect. You hear the engine struggling to run, and also check engine light has come on. If we also disconnected coil 1, for example, the misfire gets worse. Yeah, and you are going to get fault codes for every time there is a misfire. you get oxygen sensor, you get codes that point you toward the cause of the misfire, but you also get a code that tells you there's something wrong with the air fuel mixture. The O2 sensor circuit, no activity detected, blah, blah, blah. That's to do with the, and also there's another code here, system tooling. So that is an indicator. And every time we know in this case, for example, the misfire was caused by disconnecting coil to cylinder 1 and 4. Even if we cleared the codes now, they simply come back. Have you noticed that? Before you solve the problem, even if you clear the faults, you are wasting time. Even if you clear the code, you are wasting time because the fault comes right back. But now let's restore cylinder number 1 and cylinder number 4 and clear the fault codes. You see now you don't have any codes and everything is running dandy again. Even the codes for RPM have disappeared. So, and the one for oxygen sensor. So they are related to the misfires. Right? What else can we play with again here? I'm not sure. Yeah, switching the fan off. That's the connection for the cooling fan. Oh, no. That's for the throttle control valve. Let's try to depress the throttle, the accelerator pedal. Yeah, you don't get a reaction. Yeah, so if we went to read fault code, we shall read the code that says idle RPM higher than expected. Let's put the connection back. Let's put it open. Check engine light comes on. Put it back. Restore it. Check engine light goes away, and you can now control. And the code has now gone into history. So we clear it, and we don't have a problem. Let's try to disconnect the fan, cooling fan. You not immediately get an issue, but I believe you should be able to get a fault code for that. Not yet. I think it will check the circuit when it wants to, when the engine warms up enough and the computer wants to turn on the fan. That's when it will store the code. The same thing for the evap system. Let's see what happens when we play with the EGR valve. We've disconnected it. Let's check for fault codes. Not yet, until the engine wants to restore, wants to operate the EGR valve. That's when it will set a code, I believe. Let's run the. Do you notice that every time we raise the RPM now, the check engine light goes on? So it probably has set a code for EGR valve. Yeah, you can see it now. It has a code for the EGR valve. Let's restore it. Clear the fault code. Play with the RPM again. This time the check engine light doesn't turn on again, and there is no fault code. Yeah, there really is here. Oh, before we go to the release, there is a mass here. If we disconnect the mass airflow, I think the engine will stop. No, in this case it is continuing to run, so the computer went into default mode, and it is looking at the map sensor. I believe it is looking at the map sensor and the accelerator pedal position sensor. Come up with values for calculated mass airflow, but that is not so accurate. That's why a car with a faulty mass airflow circuit will consume a lot of fuel. It will continue running, but will consume a lot of fuel. You can see the check engine light is on over there. Let's go back, try to read the code. You can see a code for mass airflow on top, accompanied by one for oxygen sensor and system tooling. Let's restore that. Should we disconnect the battery? I think not. It's not a good idea. What else can we play with? Yeah, I think that's enough playing with the diagnostic scanner. I'll put it back in storage. But while the engine is running, I'll show you some other things. We have wiring diagrams here. If you are a professional that is going to be working on cars, you always need resources like this wiring diagram for the vehicle you are working on. Every vehicle is different, so every vehicle has a different wiring schematic. Even amongst the same brand and same vehicle model, you can have a Toyota Corolla 2011. You could have one with a 1.3 engine, maybe one with a 1.5, another with a 1.8, and maybe a 2-liter. Those are going to have different wiring schematics because they are different. They may look, to the untrained eye, they may look similar, but they are not. So some may have components that the others don't have, and that's where the differences are going to come in. And you need these schematics to follow the circuits to troubleshoot them. For example, if you found out that the mass airflow, you're having a mass airflow fault code, you are going to come, I think this is a mass airflow right here, the one that I have highlighted. You will see that it has 1, 2, 3 wires. So if we come here, you see the mass airflow has a blue, an orange, and a green wire, and those are indicated here. It's not blue actually, it's what, violet, gray? Yeah, if you look, yeah, it's not blue, it's violet, grayish. Yeah, so if you come here, the violet, that violet wire is the one that supplies power to the sensor, and then the green wire is common to other sensors, so that must be the ground, this one, and then the orange wire must be the signal going back to the ECU. This is the ECU in the wiring schematic. Yeah, so it's important if you are troubleshooting, because if you have a fault code for the mass airflow, for example, you are going to come here at the mass airflow and check before for you to determine what's wrong with that circuit. You are going to come here, which is at this the component itself, and test, and then also come and test here at the computer itself. For example, at the shared power. For example, if you don't find power here at the gray wire, if you come here on the mass airflow and test it, and you find no power, then you have to follow this wire back to the computer where it comes out of the computer. If there is power here, but there is no power here, then there's a problem with the wire. So now you start looking for the open part of the wire, and so on. So for those of you who are already in the industry, who see, for example, mass airflow code, mass airflow sensor code, and then go ahead and just swap sensors at the customer's cost without testing, without correct testing, well, you are costing the customer money, and believe you me, if the customer finds a better trained mechanic, I doubt they will be coming back to you. You are slowly bleeding business. So that's why you need to get training like this. We are no longer in the age of guessing what the fault is. With this information right here, this education and access to equipment, you shouldn't be doing this to customers' cars. So that was an example of how useful a wiring schematic is. So this is a full wiring schematic for this engine, at least for the components that are shown in the simulator. So let's close that. Our engine is still running. Must be hot now. Yeah, look at the temperature. So let's play with the multimeter. have a multimeter here. Remember what the wiring schematic was saying. Let's bring the wiring schematic back. For the mass airflow, I have the mass airflow here. I have the multimeter here. And I have the wiring schematic. So let's say I want to determine if what is on this wire, this gray purple wire. I want to check if it has battery power. Actually, it is getting power from the computer, so this should be 5 volts, not 12, on the gray wire. So I have to zoom out a bit, connect the black terminal of the multimeter to the negative terminal of the battery, and then let me zoom in again first, and then bring this testing lead, the red one, to the gray wire here. So I should see 5 volts here, and that's exactly what I have. So that's a good test. Now if I need to check the ground is on the green wire, so I should have like 0 volts when I go there. That's right. So because I'm measuring voltage, there is always a small voltage there because of Ohm's law. These are details you learn in the Electude classes. If I switch the engine off, it may actually become 0. Let me try that. Yeah, it goes down to 0. So it goes down to 0 because there is no current flowing here now. The system is switched off. So if I switch the engine on, there is a small voltage because the system is operational, current is flowing. You see a very, very, very small voltage, but for practical purposes, this is 0 volts. I'm happy with that. But this is the signal now. That is what the mass airflow signal looks like. If you increase the RPM, you see the airflow increases and the signal also increases. But I'm not sure whether this signal is analog or digital. So to be sure about that, I'll need to use an oscilloscope. So I'm going to dig the oscilloscope out. Oscilloscope, where are you? So I'll need to reconnect. There are classes in the Electude learning content. There are classes for how to use all of these. I'm not going to go into details, teach you how to use an oscilloscope and all that. If you need that, you'll need to enroll onto class. I'm just showing you how the simulator works for now. For details, you need to purchase a license and dig in. There is a lot of content relating to automotive repair training. So I need to switch this on. I'm using the red channel here. So this signal is analog. Why? Because I can see a straight line already. So I'm trying to let me close the schematic and bring the oscilloscope here where you can see it in view. So you are going to see on the oscilloscope, you are going to see the signal change. You can also watch the multimeter. The multimeter, for all intents and purposes, the multimeter is a more visual oscilloscope. Rather more visual multimeter. sorry, the oscilloscope is a more visual multimeter. It gives you detail that a multimeter will not. The multimeter and oscilloscope can view the same signal, but the oscilloscope will give you much more detail. So for example, here they are both reading 0.56-ish. This one is already averaging the second decimal point, the multimeter, but the oscilloscope is getting into more detail. And because I'm seeing a continuous line, that means the signal is analog. So if I were to increase it, you will see how the signal is changing on the oscilloscope. Let me play with the time scale on the oscilloscope so that you can see this a little bit slower. That is the signal. What you are seeing on the oscilloscope is the signal coming from, as the computer is seeing it, coming from the mass airflow. I could actually, if I want to see more detail, could do that. Yeah, you always want to see that first gulp for a good mass airflow sensor. Yeah, you want to see this first gulp on a good mass airflow sensor. So yeah, what else can we see? Maybe we should check on something digital. I know this cam sensor is digital, this one, but we need the wiring schematic to see which is the signal wire. It's usually the middle one, but not always. For most manufacturers, if you find a 3-wire sensor, usually many times the wire in the middle is the signal, but don't take it as a rule. That's why you need wiring schematics. So for the cam sensor, which is this one, the signal is actually, the gray one, because this orange wire is common and the red wire is also common to other sensors. So the signal can only be this one, which is the gray wire. So let's bring the multimeter and the oscilloscope. The cam sensor. So now the multimeter is saying 3.4 volts, but I'm sure that's a digital signal. So you are going to see that on the oscilloscope. So you see this is a digital signal, but the multimeter is averaging that signal and giving you a continuous reading. But the oscilloscope is able to give you more detail about that signal. You see that? That shows you the importance of an oscilloscope. There are times when only a multimeter is sufficient. How do you know? Look at the wiring schematic. And how do you obtain that information? The wiring schematic is not going to tell you everything. You must have some basic knowledge about how these components work, how these sensors work. If you have covered all these classes in Electude, you'd have no problems knowing where to go to find this information and how to use this equipment. So now this is the cam signal. I want to put the blue channel, because this oscilloscope has 2 channels. I want to put the blue channel on the cam sensor, which I believe is this one right here. Just getting the wiring schematics out to know which one is the signal. Cam sensor, inductive sensor is this one. So with this, you cannot tell right away which one is the signal, because both wires run back to the computer and they are not shared. So one is likely to be the ground and the other the signal. So let's go back to the sensor. I'll bring the blue channel here, then turn on channel 2. Okay, I need to turn on okay. Yeah, so channel 2 is also active now. It looks like this is a continuous voltage, so that looks like it's the ground. Let's try the other wire. Yeah, and now you see the screen is full of the blue signal, the crank signal. So let me first get it at the right scale. And try to move it up. Try to move it high up. Yeah, I think that's a better view. Let me reduce the voltage scale a little, leave it at that. So that's the crank sensor. So if I were to rev the engine up, you'd see both signals changing. The faster the engine, you can see the response of the sensors. Let me play with the time scale again so that you get to see. I'm using the trigger here to hold the signal in one position so that you see the changes more clearly. Yeah, so let's yeah, that's what a common crank signal, a good common crank signal on this car looks like. What else can we try with this? While we still have the oscilloscope with us, I think we can go to let's disconnect from the sensor. From the sensors. Let's go to the throttle control valve or module. If you bring out the wiring diagram, the throttle valve control module is actually a module with the valve. It's a valve with the module inbuilt. You see that it has 1, 2, 3, 4, 5 wires. One wire, this one, is for the power. Must have 12 volts on pin 1. Is that true? Altimeter wire. That is the black wire, this one. Let's see what voltage is there. Yeah, 13 volts now because the engine is running. If you were to stop the engine running but leave the switch on, I cranked. Let me stop there. Because the engine is not running now, you have 12 volts. When the engine runs, you get charging voltage over there. So now let's go to, let's take the dashboard away. because the screen is now populated. So the ground connection is this black wire. What color is this? Looks dark brown. Okay. Come here, 0 volts, and also if you move the multimeter to resistance, you can hear you have continuity and you have only 4.6 ohms. So let's go back to voltage. That is our ground. We proved it. So the other, this wire here, the orange one, is this one here. That looks like an analog signal wire. So it's reading 0.6. Going back to the dashboard. If you play with the accelerator position, you can see that signal is changing. Yeah, now I want to bring the oscilloscope back. Oscilloscope, where are you? Oscilloscope is here, but I need to reconnect it. This is a common wire, goes to the black, rather to the negative terminal. And I'm going to put the red channel of the oscilloscope on the analog signal, and then the blue one onto this other wire. If you see this, the white, green, and green wires are twisted, and you can see them here. They are shown as separate, but in real life they are twisted because they are CAN communication wires. So this throttle control valve has redundant signals, as in it sends an analog signal as a backup and then to the computer, and then also sends broadcasts a digital signal via CAN network to both the computer and other. You see this tree here? So there is a connection going to the computer and continuing in this direction and that direction. So it means those signals are sent to other modules in the vehicle for their own consumption and to make their own decisions based on the position of the throttle valve. So that's what we call redundancy. So now I want to turn on the oscilloscope. The red channel, I want to bring them to the same value. Oh, the signal on the orange wire is actually digital, it's not analog. The backup, the disconnection here, it's actually digital, it's not analog, as is the CAN network here. So the blue signals are the CAN signals. Let me increase the voltage. Yeah, so let's move this to the oscilloscope blue channel to that other side. You can see the signal on CAN, that is CAN high, it is a mirror image of CAN low. Right, so if we play with the RPM, you will not see the CAN really change, but you will see the digital signal in red, you will see it change. The digital signal, but it changes. Right, let's bring this red channel. So now, if on the red channel, both probes of the oscilloscope are on, and this is the multimeter. This is the oscilloscope. You come back here. I'm trying to get you a shot of the oscilloscope signal. I believe now I have to change the voltage scale. In that channel, and then also bring it further down so that you can separate it. You can see them separately. They are supposed to be mirror images of each other. I'm trying to separate these signals. Let me put red on top and move blue further down. Blue, channel 2, bring it down. Yeah, so now you can see them a little bit more separately. Yeah, I can play with the time setting so that you get to see more detail, more or less detail. Now you are seeing more detail. But it's not always that more detail is good. Sometimes you want less detail, so you zoom out like I'm doing now, so you see here. Now I have overdone it. Now I can go the other way. Yeah, that's a good CAN signal. How do you know? Come and enroll for Electude classes. I believe we've played enough with the simulator and strung this out long enough. Okay, one last thing I'm going to do is maybe show you command signals coming from the computer to both the ignition coil, one ignition coil, because they all work in the same way. I'll choose one ignition coil, say maybe ignition coil number 1, and then one injector. So let's get rid of the wiring schematic. With experience, sometimes you don't need the schematic for everything. These are injectors, so obviously one of them, especially if you look at the wiring, the red wire is common to all injectors. If you know anything about how injectors work, or if you look at the schematic, again, let me bring it out just for emphasis. These are the ignition coils. These are the injectors. All the red wires are supplying power to the injector. Then the computer will control the other wire on each of those injectors. Will control the other wire separately from the other injector, but they receive power from the same source. And then for the ignition coils, they receive power on the black wires. And then these are the spark plugs right here, over here. And the red, in this case orange, here blue. I think each of these wires, one of these wires, for example, this coil number one of them is a signal from the computer to the ignition coil to command a spark event. The other wire will be a confirmation. We shall find out which one is which by using an oscilloscope. How? Let me show you. Let's disconnect everything from the throttle control valve. I want to put this here. That is confirmation that you have 12-volt power on that injector, and the same on the second injector. So that wire is common. So let's play with injector number one. Let's play with injector number two. So now for control of that injector, let's use channel number one of the oscilloscope. We have a signal. We shall delve into its detail later, but also let's check which wire is the control. For the ignition coil, so blue wire, that's continuous, so that can be a control. No, orange wire. Let's try blue wire, also continuous, not control. Maybe there's something wrong with my scale. It's very low. Is it low or high? Let me increase it. It's just full of noise. What's going on here? Blue channel. Let me zoom out first. Oh yeah, the signal was always there. The signal for the ignition coil was always there. So in blue is the coil on command for coil number two, and in red is the injector command for injector number two. No, I'm actually on coil number one. Let me move the probe to coil number one. You're going to see a similar thing. So now let's zoom in a little bit more. I also move the trigger further away from the center so that you are able to see this relation. So this is how it works on this cylinder. you have the injector event, and after so many milliseconds, you have the spark event. So let's count how many milliseconds that it takes, because this is the starting of the injector squirting fuel. So this is 5 milliseconds, 10, 15, 20, 25, 30, 35. So after about 38 milliseconds, the spark event happens on this cylinder, and it's going to be the same with all the other cylinders. You have the fuel coming in first, and then you have the ignition event happening about 38 milliseconds after. How do you get all this detail? Learn how to use an oscilloscope. How do you learn to use an oscilloscope and learn all these other things? You need to enroll onto Electude class. I'm wondering if there is anything else that is interesting that I haven't shown you, that we haven't played with. We've played almost with all the sensors except the temperature ones. Maybe I will go to those, and also the fuel pump. Let's begin with the temperature sensors. I'll take the oscilloscope away because those signals from the temperature sensors are really slow, so we don't really need an oscilloscope to examine those. But is intake air temperature sensor here, for example. If you look at the wiring schematic, intake air, the brown wire is the signal, the blue wire is the ground. Let's prove that. So the blue wire is the ground. You can check for continuity. You hear that from the multimeter. So we go back to voltage. If we disconnect this, the signal is going to be, this is the signal wire, 3.42 volts. Temperature sensors are usually thermistors. Their resistance falls with the increase in temperature. That is for NTCs, negative thermistor. There is negative NTC in full. I've forgotten the full negative something coefficient. Anyway, if I bring this back here, where you are seeing 3.42, you are going to see 5 volts because the circuit is open. If I put it back, the circuit that was 3.4, that was 5 volts is now 3.42, and it will keep falling as the temperature increases. And it will, that voltage will increase with drop in temperature. That's why it is a negative. It's a negative. There's a name for it. PTC is positive. Is it positive thermal coefficient? And NTC is negative thermal coefficient. I need to double check by going back to Electude class. Anyway, you get the point here. If I were to run the simulator from raw when the engine is cold, this voltage will be higher. And when the engine starts running, that voltage will start dropping. In fact, let's turn the engine off now and wait a few seconds and see if this voltage goes down, because as the engine cools down, the voltage should actually, if it is a PTC, the voltage will increase? No. With an NTC, negative thermal coefficient, the voltage reduces as the temperature increases, and vice versa for a PTC. So it's going to take a long time for the engine to cool down. So I think what we can do in the meanwhile is let's have a look at the pump. The fuel pump is back here, in the back of the vehicle. When you turn the switch off, run again. You hear the pump running for a second. That is called the prime. It's priming for the engine to start without difficulty. It's trying to build up pressure before you even start the engine. Let me do that again. Yeah, so let me bring the fuel pressure gauge out. You can see it is at 200 kPa, but it is falling a little. The longer the vehicle stays parked, the more this pressure falls, because the pressure that was built up in the pump or the fueling system of the vehicle leaks back, drip by drip, back into the tank. And that's normal. What you don't want is to prime like this, switch off, and then the fuel pressure immediately also falls to zero. It means there is a valve in the pump that is faulty. It will not stop the engine running, but it will lead to long crank times. So let me disconnect the pump. You can see the pressure is still there, but I'm going to crank the engine. That will consume the fuel in the fuel lines, and the pressure will fall almost immediately. Let's try that. That's what happened. That's why the car is not even starting now. Now, if I were to connect this and switch on the key again without cranking, without starting the engine, the pressure is going to go up. You heard that. That's the prime. Now, when you start, the vehicle runs immediately. You can see the RPMs here. If I disconnected the pump, the engine dies and the pressure falls. So let me turn the pump, and this time I'm going to crank right away without priming, and you'll notice that it will take a little bit of time. It will take a little bit longer for the engine to start running because it has to build up fuel pressure first. Let's do that. Yes. And also, when you have a good pump, whenever you go hard on the RPMs, whenever you raise the RPMs, the pressure doesn't fall. If you have the fuel gauge on, the engine is running at idle, and you increase the RPM and the pressure falls, that means you have a weak pump or some restriction in the piping. Yeah, I think we've played with that. And you see the voltage here is increasing a little bit. That means it will take a long time to get back to zero, but at least this increment is showing us that this is an NTC. When the temperature starts falling, the voltage increases. That's the point. And let me switch this off and wait. Then we are going to, I think we've done almost everything that I wanted to show you with this simulator. I think the video is long enough. Yeah, if you want to play with the simulator yourself, you are welcome. It's free.